We are studying one-dimensional harmonic oscillator in quantum mechanics, and this is the last lecture, and I will focus on the properties of the generating function, or with another name, on the coherent state. But first, let me just remind you of what we did. This is the reminder. First, we solved the Schrödinger equation analytically through a series solution. Then we again continued analytically and found the representation of Hermite polynomials in the complex plane. And then we studied the generating function of the Hermite polynomials, and we found the recursion relations. From recursion relations, we went back to the differential equation. So you can play with those things in the analytic solution. Those were the first two lectures. In the third lecture, last time, we studied algebraic properties and algebraic solution. And it is because this Hamiltonian can also be written as a dagger a plus 1/2, and a is a annihilation operator, x plus ip, x and p being operators, √2, and its Hermitian conjugate, a dagger equals x minus ip over √2. And this is an important combination, which we call the number operator. Number is equal to a dagger a. And we constructed the states of the number operator. And so if n is an eigenvector of a dagger a, with n, then the energy eigenvalues are n equals n plus 1/2. And n was restricted to 0 or positive integer values. And this is called an annihilation operator because corresponding to the lowest state, there is a state 0, and this is the ground state of the harmonic oscillator, such that a0 is equal to 0. And in the coordinate space or in the momentum space, we solved it. And for example, psi 0x was 1 over pi 1 over 4 e to the minus x squared over 2. And same with the momentum, replace x by p. And then we constructed these states. And these states were orthonormal. And we also played with the commutation relations of these operators, a and a dagger. Let me just remind you again. A dagger n was n a dagger n minus 1. So if you expand an operator function, if it's possible to expand it in power series, then a dagger is equal to delta a dagger f. This is one group. Another group was if we raise the power of a. So let's say ak a dagger to the n. If you work out this commutator, there will be many terms with a's on the right. But if we put 0 here, all those a's acting on the ground state will give 0. So the only contributing term will be a A K times commutators A dagger N. We can even write this much more simply because every commutator is of this form. That means this is delta A dagger K A dagger N 0. So just take this K derivative. So it is n factorial divided by n minus k factorial A dagger n minus k 0, where we assumed k is smaller than or equal to n. Then we took this form. We constructed the this generating function by lambda n root n factorial n, which is n lambda n over n factorial A dagger to the n acting on 0, which is nothing but e to the lambda A dagger 0. And this is a generating function of all the harmonic oscillator states. So one can use them for many practical purposes, which we did, which I will not repeat, but just remind you. Using the generating function psi lambda, we proved that, for example, once more that Nm was delta Nm, that these states were orthogonal. These are the harmonic oscillator states. And furthermore, we found x square in the states n. Let me say Nm, and delta x square as x square Nn minus x Nn. Similarly for p as well. And we found that, for example, this important relation, delta Pn, was equal to n plus a half. And for the ground state, n equals 0, this is the lowest possible quantum mechanical uncertainty product. All right. So that was the, this is practically where we left last time. Today, I want to focus on this psi lambda, because it's a very interesting state. This is not normalized. Psi mu psi lambda is 0 e to the mu star a e to the a dagger 0. And the important property of this is that it is an eigenstate of the destruction operator, lambda psi lambda. So replace A by lambda, because this is psi lambda, and this is an eigenvector of A with lambda. So the result is e to the mu star lambda 0 e to the lambda A dagger 0. But A dagger annihilates the bra ground state. So the only term that contributes here is the first term in its power series. So 0, 0 is 1. So it is mu star lambda. All right? So this is where we begin. So we begin from here. Let's take it here. I erase the rest. Let us normalize these functions. Psi lambda, psi lambda. I am just copying result with mu replaced by lambda, so it is lambda square. So if I divide every place by e lambda square, the result is 1, so it's normalized. So I will define a state lambda as e to the minus lambda square over 2 psi lambda, which is e to the minus lambda square over 2 sum over n lambda to the n over root n factorial n. So this is our state lambda. Lambda is a complex number, so please note that this is lambda absolute square and not lambda square. Lambda has a real part and an imaginary part. And x, its coordinate representation is this thing, e to the minus lambda square over 2. Then n lambda n over root n factorial xn, and xn was 1 over pi 1 over 4, 1 over 2 to the n factorial h and x e to the minus x square over 2. This is equal to 1 over pi 1 over 4. This is lambda over 2 raised to the power n. So we can write sum over n, lambda over root 2 to the n, h and x divided by n gets out of the square root n factorial times e to the minus x square over 2. So this is simply the generating function, gx with the parameter, we called it h before, now the parameter is lambda over root 2. We know what this is, it is e 2x lambda over root 2 minus h square, which is lambda square over 2. So this makes it. So it is equal to 1 over 4. Let's put it here, e to the minus lambda square over 2. E to the minus lambda square over 2. E to the minus lambda square over 2. This is absolute square. This is just square of this complex number. E to the root 2 x lambda times e to the minus x square over 2. And this is our lambda, x lambda. I'm erasing the rest. Perhaps we should put that up because we will use it quite many times. Okay, I'm erasing it. Now, mu lambda. This has e to the minus lambda square over 2 from the normalization, and this has e to the minus mu square over 2. So it is e to the minus lambda square over 2. From here, e to the minus mu square over 2. And psi mu psi lambda, which we showed it was e to the mu star lambda. So these states are not orthogonal. Let's take the this is the probability amplitude. Let's look at the probability that we can find lambda in this state prepared as mu square. So this is e to the minus, this is a real number, so it's simply square, lambda square, and this is e to the minus mu square. This will come with its itself and its complex conjugate, mu star lambda, e to the mu lambda star. So it is e to the minus I have the squares and I have the cross terms. Therefore, it looks something like this. Minus lambda, mu star minus lambda star. Let's check. I have the minus mu square, it's here. Minus lambda absolute square, it is here. Minus lambda mu star, with a minus becomes plus. Okay, it checks. So we found that mu lambda absolute square is e to the minus mu minus lambda square. So these states are not orthogonal, and the probability of finding lambda in the state mu is given by this. And yet these states, the coherent states, are complete. What do we mean by that? Lambdas are complete. Are complete set. We mean this 1 over pi d square lambda is a unity operator. That's what we mean. It covers the whole space. So let's see that we can compute this one. D square lambda is d lambda real times d lambda imaginary. And the lambda state is minus lambda square over 2 sum over n, lambda to the n factorial root n factorial n. So it turns out it is better to use polar coordinates. To use polar coordinates, we write lambda as rho times e to the I theta. So this is the phase of lambda. This is the modulus, magnitude of lambda. So d square lambda is rho d rho times d theta. So I will just use this here. This is equal to 1 over pi from 0 to infinity rho d rho from 0 to 2 pi d theta. We simply wrote that. Then we have sum over m and n lambda to the n over root n factorial times lambda star to the n over root m factorial. So we have to take the integral and we have to take the sum. I will erase this. There is no blackboard space, so I'm erasing it. All right, I have an e to the minus lambda square over 2 coming from this lambda and another one. And here we have a factor e to the minus lambda square. Lambda square is e to the minus, because lambda magnitude is just rho, this is e to the minus rho square. So this is equal to 1 over pi sum over m and n rho d rho from 0 to infinity. Let's put e to the minus rho square. Then I have lambda n, lambda star m. So this is rho to the n plus m, e to the I, n minus m theta. So I have rho to the n plus m. Then I have n m over root n factorial m factorial. Now I will put the theta integral 0 to 2 pi d theta e to the I n minus m theta. So unless n is equal to m, this integral is 0, and for n equals m, this is 0, so e to the I 0 is 1, so it's just 2 pi. Therefore, here we have delta n m times 2 pi. Let me carry this result here. Mu lambda square is equal to minus square, so that I will continue the calculation here. So n is equal to m. I have an n factorial that comes out. 2 pi, this pi cancels that. So equals, pi is gone. I have, and n is equal to m, so I have a sum over n from 0 to infinity. So when n is equal to m, I have rho to the 2n, or rho square to the n. So I have the pi is gone. Here I have 2 rho d rho, then e to the minus rho square, then rho to the 2n, then n divided by n factorial. Let me just define a new integration variable, eta being rho square. So the eta is 2 rho d rho. So this is sum over n, 0 to infinity. 2 rho d rho is just d eta, e to the minus eta, and eta to the n, eta to the n times n over n factorial. But this is a famous integral. This is the gamma function at n plus 1. And when n is integer, and here it's an integer because the sum is running over the integers, it is n factorial. So n factorial cancels that. So we are left with sum over n, n, and the oscillator states are complete. That's equal to 1. So despite this non-orthogonality, the coherent states, lambda, are complete. So what does complete mean? You can expand a function in that space in terms of these coherent states. I will keep the result, write the result there, but erase the algebra. Okay? If it is registered, I'm erasing. So, not orthogonal, but complete. 1 over pi d square lambda, lambda is equal to 1 operator. So we are done with this. So this is the coordinate representation of our coherent state or generating function state. And what is the mean excitation number n in this state? So a new calculation. Let us compute lambda n operator lambda. Lambda state has, of course, many oscillators and each oscillator states, and each oscillator state has a different energy, n plus f h bar omega. But lambda is like a packet of these harmonic states. So what is the mean excitation of this wave packet? And this is very easy because of the form of the lambda a dagger a. N operator is a dagger a, lambda. And lambda is an eigen state of a. So this is simply lambda star lambda. A dagger lambda gives me lambda star. A lambda gives me lambda times lambda. But this is 1. So this is simply lambda square. So I will call it n bar. The average n is lambda square. So lambda is such that lambda absolute square is n. All right. Next thing is to look at is n square. So what is lambda n operator square lambda? So we write lambda a dagger a and then another a dagger a lambda. So these are okay. A acting on lambda, a dagger acting on lambda. So I have here lambda square lambda, and those in the middle are here a dagger lambda. We have to bring a to the right. So the way to do it we discussed last time. So it is a dagger is equal to a dagger commutator plus the reverse order a dagger a, and this is simply 1. So a dagger a This is lambda square, lambda a dagger a plus 1 lambda, and this gives me another lambda absolute square, so it is lambda square times lambda square coming from here plus 1 coming from there times lambda lambda, and this is just 1. But lambda square we just found was the average excitation number, so it is n bar plus 1, which is n bar square plus n. So what's the variance? Delta n square, that's equal to n square average minus n square. I am using these interchangeably. So it is n bar square. We just calculated. It's not n square. It is n bar square plus n bar minus n bar square. So they cancelled. The result is simply n bar. So I can write these relations here. N bar is equal to lambda square and n square average is n bar square plus n bar, and delta n square is, you subtract, so this cancels the square of that, so it is simply n bar, or delta n is simply root n bar. Although we did this calculation, it's interesting to look into some more detailed way. Lambda is equal to e to the minus lambda square over 2 sum over n, lambda to the n over n factorial times n, sum over n. Therefore, n lambda is e to the minus lambda square over 2. It will pick from this sum only the n term. So let me just, and n prime is equal to delta n prime. So from this sum it will only pick n prime equal n. So it is lambda to the n over n factorial. This is a root. So this is the amplitude of finding lambda in n or n in lambda. Now the probability of finding n in lambda is n lambda absolute square. This is just the absolute square of that, e to the minus lambda square. This is lambda n, lambda star n over squared is n factorial. This is equal to e to the, now we found lambda square was n bar, so it is e to the minus n bar. Lambda star is lambda square, so lambda square, which is n bar is raised to the power n bar to the n over n factorial. But this is just the Poisson P n bar n. This is just the so the probability of finding the state n in the wave packet lambda is given by the Poisson distribution. Let's check, for example, that sum over n, Pn n, it should be 1. This is e to the minus n bar, and if you sum over n, this is n bar n over n factorial. This is just e to the n bar, so e to the minus n bar, e to the n bar, that's 1. So probability is properly normalized. All right. Next, the average n is nothing but sum over n, n times p n bar n. This is the probability distribution of n, which is given by the Poisson. Let me just write it. Poisson. This is the Poisson distribution, where p and n is just that. So to compute this average n, for example, we have e to the minus n bar, that's the first term. Then we must do this n to the n over n factorial. And this sum you can get e to the minus n bar. So if you just take the derivative of this, this becomes n times n bar to the minus 1, and multiplying it brings it back to the n to the n. So this is simply e to the n bar. So take the derivative, it's e to the n bar again. So it is e to the minus n bar, e to the n bar. So these are 1. So the result is n bar. So n is n bar. Namely, if we are calculating the average of excitation by the Poisson distribution, the average is n. All right. Let me erase. I don't need the explicit forms anymore. Once I have the Poisson distribution, basically I'm done. The next is computing n square. This is now easy. Now that we have learned this is e to the minus n bar d by dn bar, n bar d by dn bar. If you apply it to here, the first one brings n bar minus 1. That one restores the order, this n bar. Then the second derivative brings n square, and then it restores n bar to the power n. And the sum is e to the n bar. So it is e to the minus n bar d by dn times n bar. This is e to the n bar. So it's equal to e to the minus n bar. So if you take that, this is e to the n bar. I took the derivative of that, plus n bar times e to the n bar. So these guys cancel. So this is n bar square plus n. So this is the n square. So n fluctuation square, which is n square minus n square, is n bar square plus n bar minus n bar square. That's equal to n bar. So that was another view, but of course the results are the same. This is just n bar in state lambda. This is n square state lambda, and this is the delta n square lambda, and this is delta n. All right.